day 2, and we are starting with basic concepts of deep learning. Right. So now, why we are learning deep learning? That is the very first question. So if we consider the simple representation, then we can say that artificial intelligence is nothing but it's a way one of the way of experimenting or researching on science. Okay. And now machine learning is way of doing artificial intelligence, and deep learning is nothing but one of the way of doing machine learning. We can say like this. Okay. So in formally we can say that deep learning is nothing but it's a class of algorithms. It's a approach of doing machine learning in a structural way. Right. So now before we go further, we will also talk about deep learning applications so that we can get motivated. Why do we need to learn this particular domain? And before I start with this details, I just want to highlight that this particular domain contains a lot of concepts, and the concepts are more important for this particular domain. Why? Because there is one thing which is called nothing but hyperparameters. Parameters which we as a programmer can manage. So only thing in deep learning which can do is nothing but how to manage this hyperparameters efficiently. And in order to do so, we require concepts. And therefore, this is the talk for it, right? Because if you are slightly familiar with this particular domain, then researcher will say that I have done some experimentation, and for this particular number of neurons, for this particular settings, I am getting accuracy of 97%. No one will ask him or her for rigorous mathematical proofs why this particular setting is only giving you this much nice accuracy. No one will ask that, right? So it's a domain where you can get very beautiful results if you know how to play with these hyperparameters, if you know the underlying structure, how these particular things are working, and so on. Otherwise, most of the heavy mathematical work will be done by libraries, right? And most of these libraries are available in most of the open source variants, right? So means your work is very much less now, because all you need to do is just understand these things, these concepts, and then apply them intelligently, and then do a lot of experimentations, right? So there is no, what you say, you will try and you will learn, right? So there is no other shortcut. There is no mathematical arguments or mathematical proofs which can prove before doing experimentation that this particular setting will give you this much very good accuracy without doing experimentation, right? So all you need to do is do lot of experimentation, try, error, right? And again you will try, and for once you will get lucky and you will get a very good results in terms of accuracy or whatever your problem ask you to do for that. And then you will then, and in this process you will understand, you will get beautiful insights why your particular setting is working for a particular data set, and then you will understand that knowledge, and then you will reapply again in some different application and so on, right? So this is idea. So therefore before we directly jump into this coding part, we must understand the overall structure of this domain, and then only we can get better results, and then only we will be able to appreciate and understand why we are getting good results for a particular setting. Okay, so now let's understand some of the applications of deep learning. So the very first application is, let's say if we consider pin code number. If pin code number is written like this in a beautiful in some sense constant numbers, where 1 will be always written like this, 3 will be always written like this, 4 will be always written like this, in other words digitally printed. If numbers are digitally printed, then it's very easy to detect them, right? But what about handwritten numbers? One person can write 1 like this, other can write like this, right? Similarly with respect to different numbers, one can write 9 like this, some other can add this extra edge, and so on. So if we consider handwritten numbers, then forget about machines. They are very much difficult to even for humans to decrypt those numbers, right? So therefore, this particular, but surprisingly, this particular system, deep learning systems, are very good in learning these numbers. And then if you give it a one new pin code, one new pin code, then the machine will be able to predict it with very high accuracy. We'll see one of the example today, how it works practically by doing its coding. But this is one of the motivation that it works very nicely with different variants of handwriting. If you provide it good amount of training, what is training and all those things I will formally cover in this talk. But as of now, in simple words, we can say if we give enough data, right, data availability is now very easy, right, as compared to 10 years back, right? So therefore, also this particular field is growing, right, because of availability of data, right? Second thing, the similar kind of thing you can also do with respect to checks, right? In checks also, you write the amount in numbers as well as in words, like this words and this numbers. And again, you want a system which can accurately tell you what is the amount of check which is written, right? Again, the famous application, face detection. So again, not just face detection, even if you give the same person's face in with different orientation like this, and let's say after few due to lockdown, let's say this particular person has gained facial hairs like this, then also your system will be able to recognize that this person is same, the name of that particular person is John, right, and so on. So it just does not just capture the simple image, but it also captures the hidden features in some sense, that even if, what will happen if some additional noise in the sense that additional information will be added to the image, then also it will be able to detect it very precisely, right? So we'll see this thing also. Apart from this, there are other systems also. For example, let's say you say some words and the system will automatically detect and understand what you are actually trying to say. Right? This type of systems are.
So your audio is lost. I mean, can anybody confirm from the students? Is he audible? Yes. Uh, Nepal sir, audio is lost. If you can. So he'll be joining in a while. Uh, Meanwhile, if you have any queries, you can always use the chat box for asking your queries.
I'm sorry, there was some internet issue. I have to rejoin.
Yeah.
Okay, so we are talking about some automatic system which can detect our voice, and from that it can infer what you are actually trying to say. The same deep learning can be also applicable to domain of physics, and it can be also applicable if you want to estimate population of some species and so on, right? So there are many applications. One with respect to images, you can provide the left hand side image, right, which contains a lot of noise, and the system will be able to generate a new image like this, right? It's very clear that all the noise is gone now. And you can also consider this image. Let's say this is your input image, and the system has somehow reference that it has a similar kind of image like this. It is also your input, like kind of it's there in your input data. So the system will understand which is the similar image for this particular given input, and then it will consider that particular image as a reference, and then it will provide you a noiseless image as your answer. I hope I'm audible properly. Can anyone confirm?
Yes, sir. Yeah.
Okay, thank you. So now, before we jump into deep learning, let's talk about some keywords with respect to machine learning. So the very first keyword is nothing but unsupervised learning. So what is unsupervised learning? Unsupervised means, in simple words, unlabeled. So that means for the given data, we are not going to give its description. For example, if someone gives me image of 1 and I label it with 1, then it's called supervised, because I'm giving labels to the given image or given object or given data. But for example, if someone gives me like this type of things where there is no label associated with them, and then also the system will able to classify them according to their features or their properties, right? So this object set is similar, they are related in some sense. This second set follows some pattern in some sense. This is the third set, this is the fourth set, and this is the fifth set, where you can see the similar kind of objects are put together. For example, this here we are not giving any labeled information for this data points, and all you need to do is you need to find out a line so that you can separate, or you can divide this particular set or set of objects in classes, right? So these classes are generated by the system itself, right? It is not considering any of the labeled information for doing so. It is purely based on the features, and similarly here also it is purely based on the distribution of this data points. And not just data points, it may possible not just a straight line. If you want, then you can also put a curve, like for example you can put this particular curve so that you can get a good classification in terms of your similar kind of objects or grouping, right? So for example here the data is classified into 5 different sets, right? This is my type 1, this is my type 2, this is my third type, this is fourth type, and this is the fifth types of objects, right? Okay, fine. So now supervised learning, mostly in today's talk we'll be focusing on supervised learning because it's easy to deal with pictures. And what we are going to do, we are going to provide this types of images to system, and we also provide what that particular image is corresponding to, right? So this is the image of hummingbird, this is the image of ladle, and so on, right? Okay. So now before we go further, this terminology is very much important. Whenever we have any data, let's say with respect to supervised learning, we are talking. So let's say I have a data of, let's say, 10,000 images. So out of 10,000 images, roughly, I will consider 7,000 images for my training purpose, and I will learn, right? So basically, before we go consider this thing, let's understand which type of things we meant by an intelligent system, because we had started with this particular idea that artificial intelligence is we can say it's a subset of science, then machine learning is subset of artificial intelligence, and deep learning is a subset of machine learning. So all of them are in some sense, these two things are in some sense trying to provide us intelligence. So what do you, which type of, you can say, qualities make a machine an intelligent machine? One can ask a simple question like this. So the first quality of intelligence is nothing but reasoning ability. The second one is it should be able to learn from its mistake, right, or learn any new data. The third is planning, and the fourth one is nothing but problem solving abilities, right? So we will see how our system is capable of doing this type of things, right? So for that particular purpose, we are providing data to it. Okay. So now what we are going to do, we are going to consider roughly 70% of my data into a training set, and then I will focus on this particular aspect, which is nothing but learn. What we are doing here, we'll see in a while. And then this is kind of your test. So you are going to use this second portion of your data only once. This is the most important thing. You are not going to reuse your test data. Test data you will keep aside, and you will only use it once, just to get just to notice what is your performance. So for your test data, once your model is ready after learning, then you will consider this particular test data, and then you will predict your outputs, and then you will be able to compare with the actual results, because this is supervised learning. So each data item, along with each data item, we are also providing its label. So these are my predicted labels, right? These labels are predicted by me, and these labels are original labels. And then we can compare, and then we can get accuracy, how well my system is doing. Those things we can do. So the important aspect is not to, for this two terminology, the main thing which you must remember is never touch test data, right? You can reuse training set data as many times as you want, right? Let's say I run by this particular system on 7,000 data one time. Then I'm not satisfied with my result. Then I will again run it second time, again run it third time. Every time, each iteration of this learning process is called epoch. Okay. So one epoch, two epoch, three epoch. So it's like kind of iterations, right? How many iterations you are going to do on a data set. So the more iterations you do, the more likely your probability of getting good results will improve. But there are some other cases also which we will cover. But generally, for the initial steps, it's very obvious that if you are doing more iterations, then definitely your process will improve. So with this note, let me take one simple exercise. Let me conduct one simple exercise, and then again we will come back to this discussion. So let me provide you this particular image. This is an image of an animal that we can see, but maybe most of us are seeing this particular image for the very first time. And my question is this image is an image of a particular animal named koala, right? This is the question. Now what you have done, you have generated one team, right? So all of the faculty members and students who are attending this particular workshop, they have made this particular team. So let's see which are the members of this particular team, and which are the objectives of these members. So let's say the first member is Krutika, right? The second member is Rakshit, right? So these were the students who have joined this particular meeting initially. I'm not sure whether they are here or not, but let me just write it down, right? So these are some students, and they are going to do some specific tasks. We'll see which task, but just let me write it down, the names of them. And then let's say here we have two more students like this, and finally this will again I will add Dr. Kaushal. Okay, fine. So now how this works? What is the purpose of what is the task given to Krutika? The task for her is just focus on eyes of this particular animal, right? And she needs to give one score, ranges from 0 to 1, telling Shreya whether this particular eyes are corresponding to this koala animal or not. She doesn't know anything as of now, so she will just randomly guess, right? Because this is the very first time some image is given to her, and she doesn't know how to whether this eyes belongs to a particular animal koala or not. So she will just give some random number to Shreya, So basically, these three students will report to Shreya, and we'll be having one more student, right? So let's say that student is okay. So now I can't use my name. Let's say some different student. Let's say Jay. Okay, and these two students will report to this particular student like this, and these two will finally report to Dr. Kaushal. So how this will work? So the task for Krutika is to just focus on eye features, right? And she will give some score from 0 to 1. 1 if she feels that these eyes are of this particular animal. 0 if she feels that this eyes definitely doesn't belong to this animal, right? So this is the scale on which she will give her ratings. Similarly, Rakshit's task is to just focus on nose of this animal, right? So he will just focus on nose, and he will again tell his or her tell his results to Shreya. And then Rushabh, task of Rushabh is to just focus on ears of this animal, and then tell the results, right? His prediction to Shreya, right? And then finally, what is the task of Naresh? Naresh will focus on legs, right? Whether those legs are corresponding to koala or not, and maybe Jai can just focus on tail, right? And then these three students will go to Shreya. Shreya will now analyze their results, and Shreya will give some weightage to each one of them. So initially Shreya is clueless. So what she will do? She will give equal importance to all this. So let's say for the very first time, I am providing this particular image to all the students, so they don't know much. So they will give this score. They feel that this may not be, this is a trick question, this may not be a this koala animal, so they are giving this type of dating, right? They are saying it's very less probable. 10% chances are these are the eyes of koala, 10% chances that this is the nose of koala, Rakshit says, and Rushabh also says that 10% chance that they are in group, and they are kind of having mutual decision that they are going to give this type of rating. So this ratings may be different also, right? So Krutika may give 0.2 and so on. So now what Shreya will do, Shreya, again, this is the very first time she is getting this type of data. So she will task for Shreya, right? So again, first I need to give a task for. So for this for the first layer, we know which tasks are there for each student. For Shreya, task is to say whether, based on these three features, she needs to say whether the overall face belongs to this particular animal, koala, or not, right? So for that purpose, she will use this information of eye, information of nose, and information of ears. And maybe what she can do, she can give 1/3 weightage to all these features. So she will give 0.33 weightage to eye, then 0.33 weightage to nose, and 0.33 weightage to, let's say, ears. And based on this, again, she will get one number between 0 and 1, and that number will be provided to Dr. Kaushal. And similarly here, task of this particular second student is nothing but to identify and say whether the remaining structure is body of this particular animal, koala, or not, right? So again, this is the very first time Naresh and Jai are doing this kind of work. So say they will again give some random score for the very first time, because very first time they are seeing this particular image, and this particular person, again, the task for his is to just identify whether the given structure is body of a particular animal, koala, or not. And again, this is the very first time he is doing, so again he will give equal weightage to legs and tail. So 0.5 into legs plus 0.5 into tail, let's say. And now based on this, scores will be calculated. So let's see what score we are getting. So 0.1 into 0.1 into 0.1, some sense equal importance is given. So finally, Shreya will provide, if we put these values in this particular equation, 0.33 into 0.1, 0.33 into 0.1, 0.33 into 0.1, then again we'll get back nothing but 0.1. So this 0.1 will be given to Kaushal. What is the meaning of this 0.1? 10% chances are this particular face is of koala. This is what Shreya is telling to Dr. Kaushal. And similarly, if we this particular second student will also say about his findings. right? And he will say with 0.2% chances, that means with 20% probability, this is body of a koala. Now, Dr. Kaushal's task is to give me the overall answer. So what he will do, he will again, very first time he is doing this kind of task, and again we are assuming all of you are not supposed to search on internet. You don't have knowledge of this. This is the very first time you are seeing it. So what he will do, he will give weightage. Let's say it's the very first time, so 0.1 is nothing but it's for face. So he will give 0.5, means 50% weightage to face and 50% weightage to, let's say, body. So based on this, he will again give me a score. So now the final score is nothing but 0.5 into 0.1 plus 0.5 into 0.2, right? And this is the score, and the score is nothing but 0.15. That means with 15% probability, this is the image of koala, and this is the result of Dr. Kaushal. Now what will happen? You all can't communicate with me. Only Dr. Kaushal will communicate to me his answer, and I know whether this particular image is of koala or not. So now Dr. Kaushal will call me and he will tell me that my result is no, it's not koala, because this probability is less than 0.5. So it's very less likely that it's a koala. But I will tell him, no, it's actually koala. So what you need to do? Go and explain your team to redo their work. So now Dr. Kaushal will again come back to you. He will first ask Shreya and Vanji that this, if you get this type of things with respect to face and body, then you must say that it's image of it's a face of koala as well as body of koala. So Shreya will then contact these three students, Krutika, Rakshit and Rushabh, and tell them that, so this is nothing but what we are doing. The error which you have got, you are propagating that particular error backwards, right? So now, okay, sorry, let me use some different color. Okay, so now Dr. Kaushal will first communicate to Shreya and Vanji, and then these two will communicate with Krutika, Rakshit, Rushabh, Naresh and Jay, so that they can adjust their ratings accordingly. So the next time when they see this type of image, then their guess becomes more accurate. And this process will repeat for, let's say, 10,000 times. So different types of images will be provided to you. For example, next time I will give you this image and I will say this is koala. Third time I will give this type of image and I will say it's koala. Fourth time I will give this type of image and say it's koala, and so on. So after, let's say, 10,000 steps, what will happen? After some steps, you will become intelligent with respect to this detection task, right? Now what will happen once? Okay, so let me explain you. Okay, so let me consider one particular image. Okay, fine. So now after some let's say after 10,000 iteration, what will happen? The very first person who is giving result for face, which is nothing but Shreya will observe that if we consider these three features, eyes, nose and ears, then importance of nose is very much. Why? Because this nose is very much different as compared to other animals. These things she will learn by her experience of this training. 10,000 times we have repeated the same process. So now she will change her weights. She will say, now I will give, let's say, 40% weightage to nose. And then she will also observe that eyes are also important, right? They may slightly different as compared to other animals, right? And in colors also. So she will give more weightage to eyes also, right? Like this, and she will give remaining weightage to ears. So now this she has learned. So these are improvements which she has done. Similarly, the person who is detecting body of this particular animal, he will also learn that whether legs are more prominent feature or tail. So accordingly, he will adjust his formula of giving results to Dr. Kaushal. Now he will give more focus to legs. So he will say 70% legs are important, only 30% tails are important, because tails are not visible most of the times, right? As you can notice, right? Tail is not visible, right? So this type of changes he can do. And then finally, Dr. Kaushal will also observe that if over the period of time, by repeatedly seeing number of pictures, he will understand that in the overall picture, the importance of face is higher as compared to body. So accordingly, he will adjust his formula. He will give now 60% weightage to face and 40% weightage to body. And over the period of time, accuracy will improve. And now if I give you a new picture, then with high accuracy, finally Dr. Kaushal will tell me whether that particular picture is of koala or not, right? So this is nothing but in simple words, understanding of neural network. This is what neural network does, right? So basically each circle is nothing but one neuron, and task of each neuron is independent of others, right? So what Krutika is doing, Rakshit won't do, right? Similarly, what Rakshit is doing, Rushabh won't do, right? And they are communicating, right? So Krutika, Rakshit and Rushabh will communicate to Shreya, Shreya will communicate to Dr. Kaushal, and so on, right? So communications are going on in forward direction. Then what is the task of Dr. Kaushal? He will analyze the result, right? He knows what is the actual answer in some way, right? And then he will again, because whenever we talk about supervised learning, like I mentioned earlier, we are always going to provide labels. So with this particular image, we are also writing down it's nothing but koala. So this information is with Dr. Kaushal, and he will use it so that the error, if it is made in the prediction, that can be rectified. So now we are going backwards. It's called back propagation, right? So we'll see these things in detail, but this is the overall idea. So now one can ask, if this is what we are doing in deep learning, then what is the difference between distributed learning, right, or distributed computing versus deep learning? In distributed computing also we are doing the same thing. Here we have one major task. One major task is there, and we are dividing into subtasks. Yes, subtasks are again independent of each other. And then what we can do, we can assign different machines for this subtask, and then we can combine the results and we get the answer. So then what is the difference? The difference is, in the case of distributed computing, we are saying these are your subtasks. But in the case of deep learning, the system itself will identify what is supposed to be done by each neuron, right? So here we are not saying that Krutika, your task is to detect eyes. Krutika herself will decide what is her task, which feature she will identify, which feature she is going to consider and repeatedly notice throughout the training process. Similarly, Dakshit, right? Dakshit himself will decide what is supposed to be done by him, right? So each neuron will. So this is the biggest difference which you can understand and appreciate between distributed computing and deep learning. And this is the major difference between machine learning and deep learning also. In machine learning, you are supposed to say these are the features, these are the feature vectors, understand them, learn them, and then predict. Here we are not doing anything like that. We will be just giving these images. System itself will figure it out which features are important, which features are supposed to be considered, and at what magnitude, that also, right? So I hope you understood this simple notion of neural networks. Right? We'll go into details more, but any queries with respect to this example?
Sir, I have one query.
Yes.
How other fellows would be knowing that this particular fellow or a system is detecting for eyes? Because if everything is done on its own, then will there be a communication between them?
Yes, there will be communication. So we'll see these things in detail. This is the just what you say, brief, simple understanding of neural networks. This is how it works.
Okay.
So we'll go in the details, then it will become more clear how it's doing actually. We'll also take formal examples, right? And then we'll actually do this task, and then it will become more clear. Okay. Okay, fine. So let's go into details. Then it will become more clear. Okay, fine. So consider this data set. It's called Hello World of machine learning, right? So it's nothing but you can see it's a collection of images which are handwritten, and this MNIST, it's called MNIST database. M stands for modified, right? Modified National Institute of Standards and Technology dataset. So what is the idea of this dataset? All the images are of size 28 cross 28, right? So it's like this, not 28 cross 28, right? This is the size of each and every image, and each image contains handwritten numbers, right? So you can see the very first row contains different ways of representing zeros, right? So it depends upon which person is writing this particular image. The person can be left-handed or right-handed, right, and so on, right? Some will make this type of circles when he or she is writing to, some won't, and so on. Okay. So now this is the data set, and if we don't have this concept of deep learning, then this is the traditional way of detecting these numbers. So for example, if you have number 7, then you will look for this type of things, whether horizontal line is present or not, like this, then whether the diagonal line is present or not, whether they are meeting at this particular point or not. But then again, when you see, you can make this type of set of rules. This is my rule 1, this is my rule 2, this is my rule 3. They are called expert systems, right, formally. So expert systems are nothing but they are rule-based systems. They will follow some strict rules, and based on these rules, you are supposed to answer whether the given image is of 7 or not. But it may be possible that someone put this additional horizontal line in 7. So at that time, again, you need to modify your rule, and then you may improve upon your accuracy and so on. But this is about images. What will happen if I provide system X-rays? So at that time, the task is very critical, and also every time you can't go to the leading, you can say, leading doctors of the world and ask them to write down rules of detecting tumor in the brain based on some reports, something like that, right? So those type of things will be very difficult. And consider a system which is trying to automize, let's say, automize, let's say, systems associated with traffic of airplanes. So at that time, if you just follow rules, then if you encounter a new scenario, then it will be very much difficult for you to give the answer, right? Because the corresponding rule you don't have, right? So therefore, these systems are good rule-based system, but they are not giving us the desired accuracy for many of the problems, right? So therefore, there is a need of this deep learning. So why it is called deep? Because it's like there are a number of modules of this particular concept, and we are putting them module like this, one above another. And now we are at this top of this particular building, and now we are looking down. So when you look down, you will say how deep it is. So therefore, it's called deep learning. If this idea was followed, like this standard horizontal representation from left to right, then maybe we could call it right learning or maybe left learning, right? But the terminology is like this. We generally club this submodules like in this manner, bottom to top manner, right? So therefore, it's called deep learning, right? So let's consider the idea of MNIST dataset. So what will be the idea of MNIST dataset? So again, we'll be going in the detail after maybe 15-20 minutes. But as of now, I have this image of size 28 cross 28, and what I want in my output, I want. So each image is of one number. Number can be from 0 to 9. So I want this type of thing. In output, I want 10 values. And let's say this image is of 4, then 4 will fire. This particular neuron corresponding to 4 will fire, and it will give the highest value. Fire means it will give the highest value. And the system will say the probability of this digit of being 4 is the highest one, right? So this is what I expect. And the next question is how to give this input, because this is my 784 values, and it's a two-dimensional array. So what I am going to do, I am going to flatten this array, right? So flatten means I will convert this two-dimensional array into one-dimensional array. How? First I will copy paste the first row, right, in column manner. Then I will copy paste the second row, and so on. So first I will write down first row, then I will write down second row, then I will write down third row, like this. And then I will feed the entire one-dimensional array to my network. How this network works, this we'll see soon, but this is the idea. This is the idea of input and this output. So now from this terminology, you will understand why there is a notion of hidden layer. Why some layers are called hidden? Because if you are at top, let's say you are at the you are standing here and you are looking down, then in between layers you won't be able to see. So therefore they are called hidden layers. Okay, fine. So now let's understand the classification formally. So what is classification? Let's say I provide you some list of objects, and they have two properties, two features, let's say length and weight. When based on them, you will characterize whether this particular object is banana or let's say grapes, right? Based on these two features, length and weight, right? So now what you need to do, this is a standard, there will be significant difference if we consider these two objects, and then we'll be able to differentiate between them. But sometimes the difference is not that much. So at that time, you can also not just straight line, you can also identify this type of curve so that your classification works. But now one can ask, if this type of distribution is given, then which curve you should follow? Which curve will be more appropriate? This one, where I am focusing on this first object of type circle. So basically there are two types of objects. The first one is circle. First one is denoted by circles. So circles are of similar kind. And second one is they belong to a same group. Let's assume circles are banana. And second one is, let's say second one, which is nothing but, let's say, grapes. Right? Second object, grapes, represented by squares, blue squares. So now one can ask whether you should go with this curve and classify. So now what will happen if next object comes, then we are going to classify bananas correctly, but it may be possible that you are classifying grapes incorrectly if we follow this type of things. Here we are focusing more on circles. All the circles, if you focus, then all the circles are covered with this particular curve, right? This particular boundary curve. So it's good in that sense with respect to bananas. If we follow this curve, then we are giving more importance to grapes, right? As you can see. So again, you can consider relatable objects also, where this type of problem can occur, right? Comparable objects where the gap between weight as well as length is not too much, right? So, or maybe some other parameters, right? It's not that this two, the first y-axis is corresponding to length and x-axis is corresponding to weight. It can be possible that we are considering some different feature 1 for this and feature 2 for this, and for some combinations there is for some data sets this can happen for sure, right? And then what you need to do, again, it's a policy decision whether you want to give more importance to object 2 or object 1, and then accordingly you decide. Okay, so now let's start formally. So now, what is concept of neuron? So if we talk about our brain, then our brain contains these neurons, and they are extremely complicated, right? They have this nucleus, dendrite, cell body, axon, and so on. So there is no way on any scale we can replicate the behavior of actual neurons, right? So what happens here, briefly, if we try to understand, then using dendrite, this particular neuron will get some signals from our body, right? So signals will be transmitted, right? So in some sense, inputs will be transmitted to through this dendrites, and there are many dendrites, right? So many inputs will be given to this particular core part of your neuron, and then based on its importance, the nucleus will do some chemical reactions, some process, biochemistry is involved drastically here, and some after some complex processes, depending upon the importance of this input, it will give some impulses, and those impulses, if they are significant, if they exceed some threshold, then some actions will be taken by us. Those type of signals will be generated then to conduct for the conduction of some action. For example, this particular session is going on, and if you find it's extremely boring, then after some time you will be thinking about leaving, or you may leave this particular session. So that is nothing but your brain is processing the inputs which you are getting from this particular session, and then depending upon the importance you give or the weights you assign to different inputs, right, you will analyze different parameters of this particular session, whether the topic is relevant to me, whether I know this particular topic already or not, do I have some other important work or not. Those type of things are going on. So while you are learning deep learning is already going on inside your mind, right? And then you will decide something. Either you will continue with the session and understand everything and ask questions, or you will leave, something like that, right? So based on these things, right, the model of perceptron was designed. So now there's no way we are going to mimic the exact things which are going on neuron on any scale on this particular model of perceptron. It's like we are considering one bulb, and we are saying that this bulb is nothing but sun, right? It's like that. Whenever you are saying that this is neuron, at the time we are saying the same thing. We are saying that we are actually mimicking or in some sense simulating the working of real brain, but no way we can do it on any scale. Why? Because if you could just consider this particular example, for we don't actually in real require this much work. We just see image once and we get all the important aspects, all these things. We don't require this much efforts, right? With just one image, if I tell you this is koala, you will understand it, right? You got it. Next time if I ask you whether this particular image is of koala or not, and even if I give you a different image, you will be able to give me the answer within seconds, and that too with utmost precision, right? So there is no way we can match it. Right? This neurons can't match the actual brain. So that's what I am trying to convey. Okay, fine. So now, what was the idea? So now let's ignore the terminology and let's focus on the actual aspect which is going on. So again, just like brain, here also we have collection of neurons, and this multiplication sign is very much important. Often in some of the representation, it's not there. So what we are doing actually, we are getting set of inputs just like brain. Each input, corresponding to each input, there is some weight associated with it, right? So these weights are nothing but they are real numbers as of now. So basically we are talking about 8 real numbers here in your 4 inputs and your 4 weights, and then this input will be multiplied with weight for all of this, right? So you will get I1 W1, here you will get I2 W2, then you will get I3 W3, and then you will get I4 W4, and then you will add these things. So you will get some number, and then you will decide your threshold. Let's say if your final answer is greater than 0, then you will do some process, otherwise you won't do, right? So this is the idea of simple perceptron model. But now it's called neuron, not perceptron. And there are few more things which are associated with it. So one of the thing is, what is the concept of bias then? So you can see bias as nothing but one more input which you can add to your neuron, right? Your neuron network, right? So because when you consider more than one neurons, then it's nothing but collection of neurons, right? And then we'll talk about neural network, right? So here one more term which you need to understand is bias, where you can, as of now, you can think it as additional input to adjust this threshold. You can think like that. And then there is one activation function, right? So what is the purpose of this activation function? Again, whether depending upon one of the famous one is ReLU activation function. So what is the idea of ReLU? It's nothing but maximum of 0 comma b. If my input is b, then this will perform this task. So that means if your input is negative, then it will give 0 as the output. Otherwise, it will continue your output, right? So if b is coming out of this neuron, then what will be the idea of this neuron? It will check with this activation function. If value of b is positive, let's say 5, right, then it will continue with 5. But if value of b is, let's say, minus 5, then this this value function will give 0, because it's nothing but maximum of 0 comma b, right? So this is the idea. Okay, fine. So now next term is representation. So in some of the reference books, you will find this representation. But whenever you see this, you need to understand this is actually this, because the most important things, which is nothing but weights are missing in this particular representation. And whenever you are looking like this, you must understand we are not just passing these weights, we are actually multiplying input with weight. So this understanding is important whenever you see this type of diagram. So not just inputs. So this notation is very abused here, because you are not even writing down weights, because weights, based on weights only the performance will change, because now input is static, right? So you can't change your image. Image will be as it is, but how much importance you are going to give in each input, that makes the difference. So therefore, so again, you can think about this neural network, right, where networks are connected with neurons are connected with other neurons, right? And each neuron has, in this particular case, an activation function. So now there is a concept of fully connected layer. What is the fully connected layer? So I am saying that layer 2 is fully connected. What is the meaning of it? Layer 2, I am saying it's fully connected. As you can notice, all the neurons of layer 2 are connected with all the neurons of layer 1. So therefore, it's called fully connected layer. If a layer 3 is fully connected, then what will happen? Each neuron here, you can, let me write it down, N1, N2, N3, then each one will be connected with all the neurons of previous layer, like this. So then we can say this layer 3 is also fully connected, if this is the case. Okay, fine. So that is the notion of fully connected. So here we are just seeing different terminologies, because if we don't understand these terminologies, then we won't be able to code properly. So that's why this is very much important, because it's important which things are under our control, which things aren't. For example, identification of features is not within our control. It's done by the system, right? So, but at what rate the system will learn how to make this particular system to work in a better way, those type of things we'll see, right? Better way means efficiently. Okay, so now again, let's again go back to the original bottom-up representation of this thing. Then this particular first, where you are providing input, this particular layer is called input layer, right? This particular last layer is nothing but my output layer. Sorry, so it's basically, I'm pointing to this. Okay, this is my layer 3. So layer 3 is my output layer. Layer 0 is kind of my input layer, and in between layers are kind of hidden, right? So output layer, so you can see this particular diagram is not symmetric. Why? Because your output layer, which is nothing but your layer 3, contains neurons. It contains computation, but your input layer doesn't contain any neurons, right? So this particular structure is asymmetric, and in between layers are nothing but it's hidden if you are looking at from the top. So this layer 2 will be hidden, layer 1 will be hidden, right? They are called hidden layers, right? So this is the idea. And again, you can notice this particular layer 2, can I say it's fully connected? Is layer 2 fully connected or not? And what about layer 3? Is it fully connected or not? So layer 2 is fully connected because all the neurons from layer 1 are connected to it. And if we consider even layer 3, then it is also fully connected because all the neurons of layer 2 are connected to it, right? Okay, fine. So now this is about activation function. So this is called rectified linear unit. I already explained it to you. So if your input is positive, then it will give you the same result. Otherwise, it will give you 0. So if my input is -5, so that means after processing, if I am getting -5, then after going through ReLU, your answer will be 0. And after processing, let's say my output is 5, then after ReLU, my answer will remain 5. So that is the idea of this ReLU activation function. So there are many other activation functions, but most of the time we'll be using these 3 only: ReLU, sigmoid, and tanh. So what is the idea of sigmoid? Sigmoid will have this S shape, as you can see, and the output will be always between 0 to 1. Right? I'm sorry for this. Some error in the pen, I guess. Okay, fine. So in the case of sigmoid, answer will be always between 0 to 1, and in the case of tanh, the answer will be between 0 to 1, right? So these two sinusoidal functions are also there, which we can use as a activation function. Okay. Now one more important term, what is softmax, right? Softmax is, let's say, after, at the very last level, we have output layer. Output layer will contain nothing but output neurons, and we will get scores corresponding to this. So let's say this is my A score, this is my B score, this is my C score. But if I add these scores, then final answer may not be 1, right? Because these scores can be anything. Like I mentioned earlier, it may be possible that A score is 5, B score is 6, and C score is 1. But what I am interested more in, I am interested in the probability distribution. Like this, if I add probability of A plus B plus C, then I should get answer 1. This is my expectation, because it's easy to understand my output if I have a nice probability distribution. So therefore, what is supposed to be done? Somehow I need to convert this 5 into 5 upon 5 plus 6 plus 1. I need to convert the 6 into 6 upon 6 plus 1 plus 5, and this 1 into, I need to convert it into 1 upon 5 plus 6 plus 1. And this task is performed by softmax. So therefore, it's important very much. Most of the times you will use it. So after output layer, you will pass your score to softmax so that you get this nice probability distribution. Okay. So now the very most important thing, how do we learn from the mistakes? How this particular network will learn from its mistake? That is the question. So let's say I provide an image of cat. Right? Let's say image of cat is provided. Right? My drawing is very bad, so I'm not trying to even draw it. But let's say image of cat is provided, and you have two classes. Let's say class 1 is corresponding to cat, and class 2 is corresponding to, let's say, dog. Okay. And after your prediction, let's say you have also applied softmax. So now I have a probability distribution actually. So now after this, let's say for a particular image, your system is saying it's dog. So your prediction 2 is close to 1, let's say 0.95, and but prediction 1 is very low, right? 0.005, because summation of this two will be 1. And now we'll compare this with our actual labels, because again we are talking about supervised learning. So along with this image, I've already provided its label that it's image of cat. So, but I have just this thing. I don't have L1 and L2. I have just one label, which is nothing but L. So now the next question is, how to have similar kind of vector with respect to label also. It may be possible that my prediction at my output level, I have 10 options. If I am dealing with MNIST data set, then I need to figure it out which number it is. So my prediction can give me 10 values, right? But my label is only one. It will say it's number one. So I need to have some mechanism which can convert this label into a vector, right? It's a very simple thing, but it's required. Then only we can calculate error and go forward. So this simple thing has a very interesting name. It's called one-hot encoding. So if you just read one-hot encoding, then it seems it's a very complicated thing, but it's nothing. What it does, let's say your output is red, and you have this. So these are the original crayon. So for the very first time when these colors were introduced by crayon, then they had used only, they had provided only this 8 colors, right? Red, yellow, blue, green, orange, brown, purple, and black. So what we are going to do, we are going to form one vector of size 8, and whatever our output is coming, we'll put, whatever our label is there. Let's say, let me explain this with respect to a simple example. Let's say my label, I have only 2 labels. So label set contains 2 options, dog and cat. Okay. So I will make one vector of size 2. The first position is corresponding to dog. The second position is corresponding to cat. And if my label is, let's say, cat, then I will say my vector is 0, 1. This is nothing but one-hot encoding. So you can see the same thing here. If red is my output, then I will represent it like this. Because probability of red is maximum, probability of yellow is 0, probability of blue is 0, probability of green is 0, probability of orange is 0, probability of brown is 0, probability of purple is 0, probability of black is 0. So this is nothing but one-hot encoding. Right? So for each label, you can have this vector now, right? And then, so how many, okay, so now one simple question, how many elements must be present in the vector, in this vector? Or maybe if I revise this particular question, then I can ask how many output layer neurons are, what should be this number? How many neurons I should put at the output layer? And the second question is, what should be the size of this vector after one-hot encoding? After one-hot encoding, each vector will contain how many elements? Do you understand the question? So let me revise this question for this data set. And for MNIST data set, my question is how many output layers are required? So the answer is very simple. How many options we have, how many different classes we can get as answer. So total we have this 10 types of images. So my output can be any one of this 10 numbers, 10 digits. So output layers must have 10 neurons. And if I represent my actual label, let's say for one particular image, I am saying it's 1, and if I represent it using a vector, then the size of that particular vector must be 10 with this values. The very first value will be 0 because 0th value is corresponding to number 0 now. First value will be 1 because the index 1 is actually present because the image is of 1, and other values will be 0. So with probability 1, the image is 1. That's what the meaning of this one-hot encoding, right? So now what we can do, we can compare this with our one. So now we'll compare here. If I do this, then I will say for this particular case, my one-hot encoding will give me 1, 0, and you are getting 0.05 and 0.95. That means this neural network is getting 0.05 and 0.95. So that means there is an error, and now we need some mechanism so that this error can be resolved, right? Error can be minimized, right? So we need some directions with respect to error minimization. This is the need, right? Otherwise our network won't work. How to minimize this error? That is the question, and is the most important question with respect to this network, right? How to minimize this error? That is the crucial question, right? So for this, what we are going to do, I try to explain you with in simplest possible words, because it's a very complicated things, and the whole chapters of reading you need to require if you want to understand it in great detail. But let me try with simple words. So consider any one of the neuron, right? So let's say I'm considering this neuron C, right? So it weights are associated with its inputs. So let's say weight 1 and weight 2. So inputs, it is getting anywhere from A and B. We can't change inputs, but we can change weights. So what we are going to do, let's consider all possibilities, all reasonable possibilities of W1 and all reasonable possibilities of W2. I am not changing anything in my network. I am just changing these weights. So what I can do, let's say I'm starting W1 with 2, one real number, and then I will explore all possibilities of W2. So W2 will range from, let's say, -2 to, so again, a real number, so it can be anything, but for simplicity, I'm consider this integers. Then next time I will increment W1 with 1, and again I will repeat the values of W2, and then again I will increase W1 and I will change W2 like this. So if I repeat this for different set of neurons, then technically for each combination of weight, I will get my error. And then, so what I'm going to do here is, I'm considering, in simple words, I'm considering different combination of weights, and for each combination, I'm listing down what error I'm getting. And if I plot it, then it will look like this. I will get this curve. What is this curve? This point represents? It represents one particular combination of weight and its corresponding error. So now what should be the task of ours? We should be able to find a point where error is minimized. In other words, we are interested in finding out global minima of this complicated curve, right? Because if we get a point, let me go forward. Okay, so let me skip this. If I reach to this kind of position, like if I reach here, then my error is minimized, right? Because this here you can say this surface is flat. I cannot go further down. So this is the best possible I can do, and the corresponding weights are nothing but my kind of ideal weight for the given task. So I need to do this. So in order to do this, what I will do, I will drop water on this particular surface. Let's say let's imagine like this. I am pouring water here, and what I will follow the direction of water. So water will, if water is touching this surface, then due to the slope, water will go, the droplets of water will flow in this direction like this. And I will continue doing so until I reach to a point where I can't move further down. And that will be the point of my interest. It will be the minima point, and there I will stop and I will get a good accuracy. So this is my task, and I can't do this easily, because what I need to do, each time I move this water point here to here, I need to drastically change my weights, and that's what being done when we talk about back propagation, right? So in back propagation, what we are going to do, for the given combination, we'll identify what is the error, what is the, then we will find out this concept of, okay, so let me first complete this concept of gradient, then we will talk about back propagation. But the idea is, this is not very easy to do, but what we are going to do, we are going to follow this particular path so that we can reach to this minima. So now how to do this, how to find this direction? So for that particular purpose, we are going to use gradient, right? So what is the idea of gradient? If we consider two-dimensional, then in two-dimensional, gradient is nothing but the whenever you find slope of this particular curve, right? If slope is 0, then at that particular time you can reach to minima or maxima, right? So now what is the idea of this? Let's say you are at here at this particular position X, and the slope is, you are calculating the slope, and it's saying if you want to find out maxima, then you go in the left direction, right? So similar thing will happen here if you are at here, but we will say no, we are not interested in maxima, we are interested in minima. So whenever the system says if slope is negative and it is telling me to go left, I will go right, and I will try to achieve this minima, right? So we'll see the exact process how this works, but this is the idea. From slope we can identify the direction, and then we can move in that particular direction. So now what will happen in each step of this? So how this particular thing works? So for that particular purpose, back propagation is required. So what is the idea of back propagation? Let's say you have designed one system. This is your network, and after that this is your prediction P1, P2, and you get some error, and then you will calculate for the given weights. You will find out what is the gradient, and then you will, based on error also, you will be able to understand how much sensitive this error is to prediction P1. Let's say P1 is corresponding to cat and P2 is corresponding to dog. And let's say it's image of cat and your system is saying, no, it's dog. So at that time, the from error, we can get a sense that it is more in some sense sensible to P1, right? Initially, definitely it's also sensible to P2, because P2 is also not working properly. It's giving more weightage to this, but this is definitely P1 is giving less weightage to this particular prediction, which is nothing but corresponding to cat. So this sensitivity you transfer to this along with the graded information. So all you need to do is you will just tell this particular neuron, so either increase or decrease its weights, little bit, not drastically. And it also depends upon the sensitivity of error, but you don't actually propagate the entire error value. You are not propagating error, you are just sending the message which is important, either to increase the weight or decrease the weight, right? Those type of things, and this thing will be repeated. So now definitely P1 and P2 alone cannot do much, because they need to again propagate this information to the previous layers, and then only the system will become more efficient. So this is the idea. So in the next iteration, what will happen? The same adjustment, so the similar kind of thing which we have discussed in the beginning, that once you get an error, at that time it will be back propagated. So the information will be flowed to this all neurons which are present at this level as well as this level, and then weights will be adjusted accordingly, and then again again we will proceed further, right? So it will reach to the very first neuron, right? So this is one thing about how this error so again we haven't seen how we are actually calculating error, but we have seen what will happen after that. If error is there, then how we are trying to minimize it using two things. The first thing is nothing but calculating gradients so that we can go in the correct direction, and then second thing, sending the information about this direction to all the neurons of your network, so that they can accordingly fine tune their weights by either incrementing it or decrementing it. So now the next question is, what will decide when will you reach to the bottom of the valley? What will decide your in some sense stopping criteria? So this is the one of the most important parameter of deep learning, which is nothing but learning rate. So what is the idea of this learning rate? So let me take this example first. So let's say your learning rate is too less. That means you are not jumping. So if we try to relate this with the water droplets, then we are rolling this water very slowly. If your water is rolling very slowly, then it may take too much time to reach to this particular position. So that is the idea of this low learning rate. So if your learning rate is very low, then you are just adjusting you are taking very small steps, and it will take a lot of time to finally reach to this particular position and get the static answer. So this is the underlying idea. Each time what you will do, you will identify this is your curve, and you will find out the gradient. You will decide whether to move downwards or not, and accordingly you will change the weights. And then finally, when you reach to this particular point, at that time the error will be minimized, which is corresponding to this 0, right? So this is the idea. But now that is the issue with this slow learning rate. What will happen if you work aggressively? Let's say my learning rate is very high. Then this was my minima, but due to my large learning rate, I took a big jump from here, point X, I went to point Y, and this is missed. And again, you need to go back. Do you understand? So this is like we are overshooting. So it's very tricky. And in some sense, it's even if your what do you say, learning rate is low, after some steps, it may possible that you get this kind of oscillating scenario where your error will go down, then again come up, go down, come up, something like that. Okay. Now, so again, let's revisit what will happen if your error rate is if your learning rate is very slow. So this is the slow learning rate. You are moving very slow in this direction, very slow, right? And now, if you move very fast, then you can see its impact. You are going from here to here, then here to here. Again, you will oscillate between these two, and you can see the accordingly how your error is going down and then again incrementing, going down. So you can see these points. Error is going down, again incrementing, going down, again incrementing, going down, again incrementing, going down, again incrementing. Right? So it's a very tricky parameter. So this we have seen, like if it is too low, then what is the issue? If it is too large, then again this is the issue. We will overshoot. So therefore, this type of things are used in practice. So what is the idea of this? With each iteration, you are going to change your value of learning rate. So initially, you are starting with some high value, then you are exponentially decreasing your learning rate as you proceed, so that chances will become very high for stopping at a proper minima, global minima. Second way is, initially we won't change learning rate at all, we will keep it high. After some time, as number of epoch increase, will decrease the value of learning rate, again exponential decrease. Second thing, stepwise decrease, right? So again we are taking some steps, right? So here for the first iteration it was like between epoch 0 to 4 it was constant like this, between epoch 4 to 8 it's constant like this, but the stepwise decrease is there. And again there is some another mechanism where we are initially we are keeping it high for the first 8 iteration, then we are stepping down, then again we are keeping slightly high for some iterations, and then again we are decreasing and so on. So again, we don't need to worry too much about this parameter also, because again system takes care of it. There is one optimizer, Adam optimizer. Generally Adam optimizer is used. So Adam optimizer will you can see its line, right? It's this one, and it after I guess most of the times after 500 epochs it will give error which is close to 0, right? So if you increase the epoch, then error rate will decrease, but again it comes with the cost of your memory consumption, as well as sometimes there is a problem which is called overfitting. So what is overfitting? So overfitting is kind of cheating. So let's say let me consider pictures. I'm again training for, let's say, cats and dogs, and let's say I have some data set where whenever a picture of dog is there, at that time dog is sitting on some sofa. Let's say sofa is there, and on sofa there is one dog, right? I assume this is a dog, right? Some image is there, this is a dog. So after some iterations, right, and let's say all the images are like this only. So whenever dog is there, it's sitting on the sofa. So now after some epochs, the system will become so smart that it will ignore the dog itself, but it will focus on sofa. So it will think that if something is sitting on sofa, red sofa, then it's nothing but dog. So what will happen to this type of system? When you give an image of cat, when cat is sitting on sofa, the system will ignore the cat, but it will focus on the red sofa, and the system will say it's the same red sofa, so therefore the animal which is sitting on this particular sofa must be a cat. So this is nothing but problem of overfitting. You have trained your system too much, and now it is focusing more on background, and it is identifying the tiny features which are less important, but the system is going to give more important to those tiny features, and therefore training it will work. For training it will work because you have provided all the data set, all the images which follows this particular rule that all the dogs are sitting on sofa for this particular data set. So it will, with respect to training, if you increase your epochs, then definitely error will go down because the system there are some smart neurons, right? Over smart neurons, I must say. There are some over smart neurons who are focusing on these tiny features, and they are passing a drastically large weight to those particular features, and because of them you are classifying fast and correctly for your training data, but when you consider your test data, you will be getting a drastic error. Right? To understand this concept of overfitting, now the next question is how to solve this. Right? So now what is my purpose? I don't want some of my over smart neurons to dominate, because if they dominate, then my system will give wrong answers because they are learning less important background features. So in order to solve this particular problem, there is one parameter which is called dropout. So what is the meaning of this dropout? Okay, so let me take one example. Let's say again, the system is kind of black box. We don't know which neurons are over smart. So what I am going to do is, let's say this hidden layer contains 10,000 neurons, and I am saying dropout rate is, let's say, 0.30. So that means in each epoch I will be randomly selecting 3,000 neurons from this 10,000 neurons, and I will disconnect them. Why I will do that? So that no neuron becomes over smart, and the importance is kind of shared. The features are kind of shared, and no one can dominate entirely the system, and other neurons also learns. So now what will happen in this epoch? In this epoch, you have, I mean, this iteration, you have disconnected some 3,000 neurons, and remaining neurons will work and they will figure out their new weights, and in the next iteration you will put back this 3,000 neurons back, but this time you will again select some different 3,000 neurons. This is just to make sure that no one gets over smart, no one gives too much focus and too much importance and too much weights to features which are very less important with respect to our given problem domain, right? So by doing this, by choosing this, again one can ask what is the ideal value of dropout, right? So again it's a question of experimentation. One cannot answer this, right? So again you need to decide which value of dropout will can give you the best accuracy for the given problem statement. Okay, so now with this what I'm going to do now, I'm going to start with this particular thing, which is nothing but our MNIST dataset. Okay, so now we'll practically apply first concept of artificial neural network. Right, and let's see how it performs. So again, this is my dataset, MNIST dataset. The size of each image is 28 cross 28, and for okay, so let me also show you the code. So mainly what we are going to do, first we will import the TensorFlow. So TensorFlow library is imported. From that we need to import this Keras library, and then this is just for plotting. This is plotting. I want to plot my images inline, just on this page only. That's why I'm adding this. Then I'm adding NumPy array. So this is nothing but just background of thing. Now the main thing starts here. The important thing is this data set is so famous that most of the you can directly download it from most of the libraries. So all you need to do is just you need to call keras.datasets.mnist.load data. So what will happen? Automatically data will be loaded, and as you can see, there are 4 names associated with this. The first name is xtrain ytrain, and the second pair is xtest ytest. So by default, it is giving me this partition. Out of 70,000 images, 60,000 images will be used for training purpose, and 10,000 images will be used for my testing purpose, right? So again, the next question is what is stored in xtrain and ytrain, and what is stored in xtest and ytest. So like I mentioned earlier, what we are doing here is nothing but we are doing supervised learning. So in the case of supervised learning, 2 things are required. If my learning is supervised, so I must provide the object, and along with the object, I must also provide its label. So here I am providing, let's say my first image is this. So I will provide this 5, right? It's a 28 cross 28 image, and I will in label I will write down its image of 5. So that means in xtrain I will have image, in ytrain I will have its label, right? So this is my image which I have stored in xtrain. This is my label corresponding to this image. This I have stored in ytrain. So initially my focus is on this tuple only, right? Xtrain, ytrain. I will focus on xtest, ytest later. Why? Because this is the test data. Again, what is stored here? Xtest has images, ytest has their corresponding labels. Okay, but like I mentioned earlier, whenever we do this type of task, we'll focus on training data first, and testing data we are going to use just once, because it's like you can't give the examination multiple times, right? If you see the exam paper, then it's not the correct way of evaluating your work, right? So let's say you already know the examination paper, question paper, and then you give the exam, then it doesn't make any sense. So it's like that. If your system sees this data earlier, then it's of no use. Then whatever we are getting as accuracy, it's of no use. So therefore, we won't touch this pair as of now. Okay, so now let's move forward. So okay, so now let me just print it down. So if I print it down, then basically okay, so before that, let me show you how it looks. So you can see this is the image of 2, and it is represented in terms of matrix of size 28 cross 28. So what will happen? So here, as you can see, it's a 7 cross 7. This is just to explain you, but if we consider the MNIST data, then it's of size 28 cross 28. So what is the idea? 0 means it's a black, and 255 means it's completely white. Okay, it's white. So you can see these values are there, ranging from 0 to 255, right? And whenever we apply this kind of system like deep learning or machine learning, we generally normalize these values. So how to normalize these values? So total values are ranging from 0 to 255. So what we are going to do? We are going to divide each value by 255. So this will in some sense help us in improving our system, right? So therefore we are doing this normalization, right? So that only relative values get considered like that. Okay. So this is the first thing which we will do. So as you can see, we have just divided X test as well as X train. Why I am just dividing train and test? Because they are containing images. So I only need to divide them. I don't need to divide my labels. So therefore I am not considering Y as of now. And if I print my first image now, then I will get this two-dimensional vector. And all the values are between 0 to 1 now. 0 dot nothing means it's nothing but it's corresponding to a black pixel. And if my value is very close to 1, that means that particular pixel is corresponding to white color. And again, this is the very first example. So we are not considering colorful images. We are just dealing with black and white images. Okay. So far we have just done this pre-processing. We have just printed this value, right? So this is the we can see this is the matrix associated with the very first image. And if we identify its shape, so just we will call this particular dot shape function so that we can get idea about the individual image size. Then like I mentioned earlier, individual image size is nothing but 28 cross 28, and using mat show function we can also print the image. So images are like this, actual data set image is like this, right? So the very first image, so 0th index means very first image is nothing but we can see it's image of 5. Similarly, if we print this third image, which is nothing but training data index number 2, then it's image of 4, right? So this is nothing but we are just verifying whether our data set is correct or not, and you can verify their corresponding labels. So like I just mentioned, the third image is 4. You can check the third index on this particular white trend is nothing but 4, and the very first image was of 5, and you can check in white trend the very first is nothing but very first value which is stored is nothing but 5. So these are nothing but my labels. So you can see that labels are actually correct. It should be, but we are just verifying. Okay. So now the stage is set. So all we need to do is we need to somehow give this matrix, right? Give this matrix of size 28 cross 28 to our neural network. So we know what neural network will do. How many output neurons will be there? 10. This is very first time I am designing a deep learning program, so I won't introduce any hidden layer, right? Let's see what will happen if we just provide, if we have just one layer, right? So this is my output layer. Output layer will contain 10 number of neurons. Why? Because our output can range from 0 to 9. So therefore 10 neurons are required in the output layer. Right? In the input layer, how many neurons are required? That is the question now. So input layer, I want to feed my image. So what is the size of the image? Image is stored in terms of matrix now. So this matrix size is 28 cross 28. And if I calculate, then basically I need to have 784 different values. So this, what is the limitation of this first neuron? It can take only one value as input. And then it will process, it will give weights to others and so on. Those type of things it can do. But for as of now, it can take only one number. So basically we have 784 numbers, 784 real numbers now, not integers, because we have divided by 255, right? So we have 784 numbers. So therefore, mandatorily, we need to put n is equal to 784. So in the first layer, I will have 784 neurons. And then I have just output layers, and output layer will contain 10 neurons. And let's see how this, how to write this basic code of doing this. So for this particular purpose, what we need to do, we need to convert this two-dimensional array into one-dimensional array, which is called nothing but flattening. I have also mentioned about this. I had also mentioned about this during the presentation. We need to first convert this into one-dimensional array like this. So first we will print the first line, then we will copy paste the second line like that. So you can notice this entry 87 is somewhere here after this initial entries, and after 87 240 will come like this and so on. So it's very simple process, but somehow we need to code it. So to do so, we are calling this particular reshape function. So when we are going to store the modified data in xtrain underscore flatten, so that we can distinguish between the original data and the flattened data. So we are going to call the reshape function. The reshape function, what it will do, it will just convert this two-dimensional array into a single-dimensional array of size 28 cross 28 cross 1. So what is 28 cross 28? So basically 784. So now, if after applying this, if you check what is the size of this entire data set is, then you will 60,000 images, all of size 784 cross 1, right? Because now you have just 784 different values. And now if you check for test data, then also it's true, because we have also applied this reshape on test data, right? So far so good. Now the most important part starts. The most important part is setup. And like I mentioned earlier, deep learning is very powerful, so you don't need to code on your own too much, because most of the things are readily available. All you need to do is you need to talk about these parameters, and you need to decide them intelligently. You need to experiment with them so that you can get better results. So the setup is done in just single line. What the setup says: keras.sequential, keras.layers.dense. So these are nothing but just call this dense, means we are going to talk about the dense network, and the way we are going to write down this number of neurons is kind of in reverse order. So whatever comes last, that we will write first. So what will come last, on the last we are going to get outputs. How many outputs we require? We require 10 number of outputs, so therefore we will write down 10 here. In between, do we have anything? No, we have just input them. So what is the shape of the input? The shape of the input we need to specify. It's nothing but 784, right? Because the image size, one image size is 784. How many times it will done, that it will figure it out by its own on the entire data set, which is nothing but 60,000. So we'll put comma and then leave as it is. Then the next important thing is activation function. Do you want to use ReLU or 10H or sigmoid? Here I am using sigmoid. You can try with anything else also. It's fine, but you need to specify which activation function is required. That's it. This model is set. Now the next thing which we need to do is we need to compile it. Whenever we compile, at that time, you can remember like this, you need to talk about losses. So for losses, we know there is one optimizer which works fine, which is called nothing but Adam optimizer. So we are going to use that particular optimizer. We have set this particular value, use this optimizer so that I can find out the minima nicely and get better results. There are many types of losses. Here I am using sparse categorical cross entropy loss. Why I am using this? Because there are categories associated with my problem. There are 10 categories, and they are sparse in some sense. Why, we will see later, but therefore I am using this particular loss function. You can use other loss functions also. You can go to this particular link and you will see there are many losses. You can also check mean absolute percentage error, mean square error, mean square logarithmic error, and so on. So there are different ways of identifying, you can say, loss or error between your predicted data and the actual data. That's what this function will do for us, right? So they will find out the error in some sense, and then the optimizer will help to reduce that particular error. And we are interested in accuracy, right? So this is fine. This is the setup, but so far we haven't provided any data. So how it works? So therefore we are fitting this model on our data. And now which data we need to consider? So this is the setup. If you just see this highlighted line, then here we haven't mentioned the actual data. We have just mentioned its size. The size of the data is 784. That's it. Apart from that, we have just derived that 10 output neurons are required, because my data has a characteristic of 10 possible object classifications. So therefore I have given 10 here, but apart from that I haven't provided data. So therefore I need to call this particular fit function so that model can actually get the data. So therefore, I am providing this X train flattened. Why flattened? Again, because the entire two-dimensional matrix it can't take directly. So therefore, I am giving this X train flattened data, and I am also providing the corresponding label so that the model can identify this loss, and then the optimizer can work and can help us in giving the optimal answer. And then I need to specify how many iterations, right? If you give more iterations, then you are likely to get good results. So let's check. I have given 15 epochs. In each epoch, it's like one iteration. It will process something and it will tell you what is the loss, what is the accuracy. So after first iteration, loss is 0.71, accuracy is 0.81. In the second iteration itself, you can see the drastic difference. Now loss is reduced to 0.30 and accuracy is improved to 0.91. Then again, after one more iteration, accuracy is improved to 92%. After few iterations, you can see accuracy is reached to, after 9 iterations, close to 93%. And if I stop here finally, then finally I am getting 93% of the accuracy on my training data. But training data is already visible to your system. It's learning on it over and over again after each epoch. So what I need to do, I need to somehow evaluate my model on test data. So therefore, what I am going to do, instead of providing it the training data, now I will provide it the test data. So test data again contains two things: the corresponding image and its label. So the label is stored in y_test. So therefore, I am providing it. And the image, again, I can't directly provide the two-dimensional image. Even if it is related to the test data, I need to convert it into a one-dimensional image of size 784. So that I have already done using XTest flatten. I have already flattened it. So I will provide this modified flattened data to my model, and I will evaluate my model on this particular test data. And I am getting accuracy of 92%. It's fine, but you can imagine I haven't used any hidden layers. It's the simplest possible model we have built so far, where I am not giving other extra neurons which are corresponding to the hidden layers. Still we are getting accuracy of 92. So that means out of 10, if I give you 10 images, if I give 10 images to this particular system, then out of 10, 9 will be evaluated, predicted properly by the system. So it's a very good way to kind of starting point to understand the power of deep learning, that even if you don't give the additional hidden layer, you are getting so nice accuracy. Now let's check this thing. So therefore, what we are going to do, we are going to just print y. So what is y? Y is nothing but my predicted output of test data. I am storing it in y, right? Okay. And if I print y, then I am getting this type of different values. Why I am getting this type of values? Because I haven't used softmax. So that means it's not necessary that if I add all these values, then I will get 1. This is an array, right? And what I need to do, if I just print down one entry, the very first entry is like this, y of 0. So you can notice it has 10 different components. First component is corresponding to 0. This is the value corresponding to in some sense it represents chances of getting 0. This is chances of getting 1. This is a predicted value of number is 1. The image handwritten image is corresponding to number 1. Handwritten image is corresponding to number 2, and so on. So all we need to do is we need to find out what is the maximum, what is the index of the maximum value. That number is represented by this y0, right? So that we are getting 7. So our prediction is saying it's 7. And later what we can do, we can actually print this particular number and we can see that our prediction is right, because our prediction says it's 7, because we have found out what is the maximum out of this 10 output values. The maximum output value is corresponding to index 7. That means the system is telling me that the number is more likely, with 92% chances, it's nothing but 7. Overall accuracy is 92% as of now. So we are saying with 92% probability it's 7, and actually it's 7, so it's good. Same thing we can repeat. We can test for second image also. The second image is actually 2, and if we apply this argmax argument, then we are getting 2. So what we can do, we can predict for first 10 data, and then we can check with our 10 data, and then we can compare, and then we can see how whether we are doing nice or not. So we can also print this type of confusion matrix, where what is the idea of this confusion matrix? 0 0 is corresponding to, let's say the image is 0 and you have detected it like 0. So 963 times that happened. That image is of 0 and you have detected it correctly. 2 times what happened? I have given image of 0, but the system is telling me it's 3. Right? 6 times what happened? Image is of 0, but system is saying it's 6. Right? And so on. You can see the dominant values are on diagonal, so most of the times the system is doing nice, but there are some errors. It's not completely perfect. You can see this is 15, so 15 is corresponding to, I guess, 4, 2. So if image is of 4, but the system is saying it's 2, like that. So still there is a chance of improvement. So let's try to improve it. So what we are going to do now, I am randomly selecting one number. Let's say I want to put 115 neurons in my hidden layer. So like I mentioned earlier, whatever comes last, that will appear first. So this middle layer will come above this input layer. So first I will write down this hidden layer neurons, number of neurons. I am putting 115. Input shape will be as it is. Activation function, this time I am changing. So this is the activation function I am giving for this particular layer, hidden layer, which is nothing but del u. And overall, I am using the sigmoid activation function, which will be used in the end when I will be getting those 10 outputs. And again, I am keeping it dense. Dense means you already know what is the meaning of dense layer. If this layer is dense, that means it will be connected, all the neurons of that particular layer will be connected to all the neurons of the previous layers. That is the meaning of dense word here, right? So this dense 10 means this 10 outer neurons will be connected to all this 115 hidden layer neurons. And this dense means all these 115 neurons will be connected to all my input neurons, which will be by default 784. Okay. And now again, I need to, so this is the setup. I have just added one hidden layer in between for that particular purpose. I have instead of one line, now I have written 2 lines, and instead of one activation function, I have used 2 activation functions. That's the change I have done. And I have already also chosen one, just guessed that this should work. That there is no rule. Why 115? Why not 107? No rule. Right? You can type it 107 also. Right? Fine. And then we have compiled it. Right? Again, the old friend Adam we are using, and again the same loss functions, sparse, categorical, cross entropy, and again we are interested in finding out what is the measure of this accuracy. And again we are providing the same data, which is nothing but our training data, which is flattened, and we are going to iterate this 15 times, and let's see the results. Right? So actually, if I run this, then it will take a lot of time. So therefore, I have already done it. It may take roughly, it depends upon number of images. So here again, images are black and white, and again they are less relatively. So still, if whenever you run this versus you run the previous model, so definitely the second one will take more time because it has more neurons. So there will be more weight parameters. So therefore more gradient descents. Therefore more back propagations. So therefore more time overall, right? So you can also check the, here it was taking 1 millisecond per step, whereas here you could notice that 2 millisecond per step. So you can see the complexity is changed. In terms of time, we are going to take more amount of time with this setup. And let's see how this works. So straight away, it is giving 87% accuracy on the training data, and loss is 0.44 after first epoch. Then it suddenly jumped to 96. So even if I run this for 2 epochs, it's better than my previous model, I can say for sure. After 8 epochs, it's already giving me 99% of the accuracy. So it's a very good result. And overall, when I stop at that time, it's giving me 99% of the accuracy. So you can see the power of hidden layer, right? Just by adding one hidden layer, we have improved drastically in terms of performance. So next is again, we are not done yet, because this we are doing, but this we are doing which is on the data set which is already available to the system 15 times. 15 times it had processed on the same training data set. So all we need to do is we need to evaluate this on the test data set. So on the test data set, we need to evaluate this particular model, and you can check on test data set, it's giving accuracy of 97. So it's again good, right? So now one can ask, this is good, but I don't like this flattening thing. Why do I need to write this particular piece of code where I am reshaping my data and then I am providing it to my neural network? Can't I have some function which can flatten my input data so that I can avoid writing this and I don't need to worry about this? So for that particular purpose, this is the solution, right? This is the solution. So you can call keras.layers.flatten. So this will automatically, just you need to provide now input shape. You just need to tell the system which type of data is going to come, right? And then you can proceed further as it is, right? So other things are as it is, like you are saying dense network is there, activation function is value for this layer, then sigmoid, then you can compile it, and then finally you can fit it, and you will get again the similar kind of accuracy you will get, right? So this is all about, I guess, this is the we have taken two steps, right? The first step is how to just start with simple neural network without any hidden layers, and for that we have observed that we are getting still nice accuracy of 92% for this data set, and then we have introduced one hidden layer in between, and then we saw how this can improve the results significantly. Now we are getting 97% of accuracy. But the major purpose of this particular talk was to make you understand these things, because it's easy to get these things, but how they are working, it's again it's a one semester thing. So I haven't explained a lot of mathematical details. I've ignored, right? And I've rushed through a lot of concepts, but still I guess you will be able to appreciate and understand these tiny things now. What is the meaning of this dance? Why we are writing in this particular order? What is the meaning of this activation function? Which other options do we have with respect to activation function? What is the purpose of this loss function, right? And what is the purpose of finally this optimizer? And what is epo, right? So this terminology is very much important. And one more thing which I would like to highlight is, in here I have skipped one thing. It's called validation error. So what is validation? So so far I have talked about just two partitions. The first partition is like this. This is my this should be my training data. Okay, so I should draw the line accordingly. So let me remove it. So okay, so this should be my training data, right? Roughly from, let's say, 70 to 80%, and this remaining thing is my test data. But you can also do this where you will be having training data, then you will be having validation data, right? And then you will be having testing data. The size of this two will be kind of same, and the purpose is also similar, but there is a restriction. So what you will do is, previously we have done, what we have done, we have just trained, and then we have finally tested. But here what we are going to do, we will train and test on validation data. We will train on test on validation data. So it's like a revision test which student can give as many times as he wants. So therefore the system can use this validation data as many times as it wants, but there is a restriction on testing data. You can't use it more, right? So now if we see this particular image, then if we see this particular image, then what it is trying to suggest is, after some epochs, what will happen? your training accuracy is improving because you can see this error line is going downwards. But due to overfitting, what is the meaning of overfitting? We already know. Now, where some over smart neurons are focusing on less important background features, and because of them, you are not performing well on your this test, which you can give as many times as you want, because this test data is it's not a test data actually, because test you can give only once. This like kind of validation data. You are trying to validate your system. You will check first. You will the similar kind of thing which will be done as you are doing in the at the time of test, evaluating the data, evaluating the system on the test data. But here the only difference is you can reuse this as many times as you want. So I can give test after each epoch with respect to this validation data, and that will give me validation error. So this data is unseen kind of, because after each iteration the system will redo and it will check for this validation, and then you can see that even for validation, due to overfitting, what is happening, the error is increasing, right? It is started to increase because of this concept of overfitting. Okay, so I guess with this note, I can stop here. We can discuss if you want to say something about this.
Yes. Are there any doubts? Anything that you want to ask?
So what I will do, I will be sharing this particular notebook with Dr. Kaushal. So he can share with you, and then you can experiment with it. So that will be good.
Yes, and also if you can, if you can share PPTs, then that would be a great help, because
Sure.
few of the students are asking about the same. So,
Sure.
yeah.
So I hope you got to learn about this. If you are learning this for the very first time, then you got to learn about this basics. So now what you can do, even if you randomly pick any paper of deep learning, you will be able to understand what's going on. Otherwise, it will be kind of completely black box. So I hope I could deliver that much to you.
Yes, sir. For me, you delivered that, because, as I said, this is the first time for me as well in terms of deep learning. I haven't learned machine learning or anything during my BTech, MTech, as well as PhD. So still, I could able to understand. So I'm pretty sure that students have also understood the parts of it, and they would be able to use it in their own research, right?
Sure, definitely.
Yeah. And I guess if there are no questions, then we can end the session over here, and we'll be meeting again at 1:15, right? Will it be okay, my concern?
I guess 1:30 will be fine.
1:30? Okay, then we'll keep it on 1:30.
Okay.
So I'll be scheduling it accordingly. Thank you, sir, for your time as well as the knowledge on deep learning, and we'll be meeting again at 1:30.
Okay, sure. Thank you so much for listening. Thank you.